So number 3 says we're going to do a spinner and a number cube in a game. Independent or dependent? Independent. Why? They're two separate things. Only raise your hand. So the spinner has an equal chance of landing on one of 3 colors, red, yellow, blue. The faces of the cube are 1 through 6. What's the probability of a player spinning a red and then rolling an even number? Steph. We're going to do that next. So let's finish 3 and then we'll do a couple of dependent ones together. And so we want to find this. We want to find the probability of a red and then an even. And I would for sure underline that in my question. How do I get a red? Kyra. 1 out of the 3 colors that there are. Perfect. How many even numbers are there on the number cube?
3.
Out of?
6. Or 1/2.
So I could, and then I'm going to do what operation?
Multiply.
So you could do either make this into 1/2 or you could find a common factor of 3 on the top and the bottom. Either way, you get the same answer. Does that make sense? Because I'm still dividing the top and the bottom by 3. 3 divided by 3 is 1. 1/6. I got it for independent events is where I want you to be.
Got it for independent.
Okay. Dependent events. Let's look at example 3. I know, but now it has to make sense. Now, there are 4 oranges, 7 bananas, 5 apples in a basket. How many total pieces of fruit are in the basket? We're going to need to know that anyway. How many are there?
Oh.
Yeah.
Me?
Yeah. There are 16 pieces. If we're going to do probability, we have to know totals. Ignacio's going to select a piece of fruit at random. Find the probability that 2 apples are chosen. Well, wait a minute. If I pick an apple out of the bowl, am I going to put it back?
Yes. No.
No, I'm going to hang on to that because I want to keep an apple, right? Is this independent or dependent? Why is this one dependent? Why, Bree?
Because what you do does affect what you don't do.
So close. Say it, Steph.
I have a question.
Hold on. So Bree said what you do the first time affects
What happens in the result?
what happens the second time. Whatever that result is, it affects it. And so this is dependent. Now, Steph, what's your question?
Okay, so the thing with the a couple days ago or something. So the one where we put it back in, the yellow or the red,
Yes?
independent,
Yes, because what's in there is the same both times.
and the dependent one is when we keep it out.
Yes. And so this person, Ignacio, is keeping an apple. He's trying to get 2 of the same thing out of the bowl. So what's the likelihood he's going to get an apple the first time? How many apples are there?
4.
Mm,
5.
5 apples out of how many? Bree said 16, right? So the probability of getting an apple the first time is 5/16. But now Ignacio's is hanging on to this apple. Well, how many pieces of fruit are in the bowl now?
15.
Only 15 because he's hanging on to one. How many apples are in the bowl if he's hanging on to an apple?
4.
And so this numerator and denominator changed because now there's only 4 apples and now there's only 15 pieces of fruit. What do I do with those 2 fractions to find the total probability? I still multiply
Really?
because I would still make a tree diagram, right? Just like I did with our chips. Only the second time, and instead of having 16 branches, I'd only have 15 branches. But I am not drawing that tree diagram because that's ridiculous, right? We just know that there would be 15, 16 times. Question? Yes. She just made a great comment. It does not matter if it's independent or dependent. You always multiply. But with a dependent event, you have to make sure you keep track and that your denominator changes because that means the total is different. When we did our game, we only had 3 chips instead of 4 chips in our cup. So it changes. Now, I'm also going to encourage you to look for the common factors on the top and the bottom because otherwise your numbers get ridiculous and you do have to put them in lowest terms. And so they divided the top and the bottom by 4, the top and the bottom by 5. It was 1/12, which is way better than drawing 16 trunks with 15 branches each, right? You see why the tree diagram is awesome if there are not very many choices, but we want to come up with, always in math, if there's a pattern, we want the fastest way to do it.
Why do you have to teach it to us then?
Because do you understand it if I just say trust me, and do you remember it? No way. No way. Because anytime I don't make you do it the hard way, Like, can you use the calculator if you don't know if you're getting a reasonable answer? And we'll eventually in 8th grade use the calculator to do a ton of graphing. But we're going to practice graphing first, because if you don't know what's on the x-axis and the y-axis, it doesn't make any sense to you anyway. Because you have to learn it, and it has to make sense to you for you to be able to use a tool.
But it's not funny to use.
Hmm?
No, it's not funny to use. It's not always present.
Yes, and I want you to know sometimes your brain is the very best tool. You're right, sometimes the calculator is the slower one. Now, we're going to do D together, because I want to practice a dependent event with you, and we're going to do a couple. So now, it's the same fruit bowl to start. What's the probability we'll get an apple and then a banana? So on your paper, I want to see D. Probability of apple,
D or D?
D, D as in dog, and banana. What's the probability of getting an apple? To start, how many apples are there?
5 out of 16.
5 out of 16. So we did some thinking before. If I am now hanging on to that apple, how many bananas are in the bowl?
7.
There's still 7, but how many pieces of fruit are in the bowl? 15, and so sometimes the numerator changes and sometimes it doesn't. The denominator in a dependent event does change. What am I doing with my fractions? I see a common factor of 5, and that's it, right? 7, I think it's 48. 7 out of 48, correct me if I'm wrong. We're good?